Good afternoon, everybody. I'd also like to thank the organizers for the chance to talk to you all today. There's been a lot of progress in developing both repeaterless and repeater-based quantum communication networks. And with that progress, there comes some great demands on the photonics. How do you route, for example, in a multiplexed repeaters, hundreds or maybe thousands of spatial modes? How do you make modulators that function at tens of gigahertz frequencies and other things? And so here, I'm going to talk about how we may leverage photonic integrated circuits, in particular using silicon photonics, which is a technology that's becoming pretty widely available using foundry services, often relying on CMOS processing, how we can use these kinds of photonic integrated circuits to try to solve some of these problems. All right, so the basic purpose, of course, of quantum communication is that we'd like to transfer quantum states over long distance. And that would be really cool if we could do that in, let's say, this kind of network, either in a metro network or in a long-haul network, because we could run on such a quantum network a great number of applications that are secure communications, which of course is the central topic of this conference, but many other applications as well, and probably many undiscovered protocols will emerge once you start having such kind of networks in place. So whether these links are based on, or whether these links are in the metro scale network where you don't need repeaters, so distances less than 100 kilometers or so, maybe a few hundred kilometers, or if you're talking about long-haul links where you probably do need some form of quantum repeater to allow you to transmit states longer distances, you need to develop new types of optics, probably. Optics that give you great phase stability. We've already heard about the need to produce good interferometers. Ways of transforming modes between maybe hundreds of different spatial modes or temporal modes. And many systems have to be heavily multiplexed. And as an example, here a couple of points in the network. Here, for example, if you wanted to do an MDI QKD link between Alice and Bob, you would need some transparent switches, at least here, and maybe here a transparent switch that is an interferometer going to a photodetector. But you'd like this not only over one channel, you need to be able to talk to many channels, for instance, in a metro network. And so you need advanced routers and switches to make this possible. In the case of quantum repeaters, to make the quantum repeater scalable, you need to interface with many quantum memories, for example, with many atomic-type quantum memories. And that, too, requires multiplexing. It requires somehow to deal with large numbers of modes, maybe hundreds or thousands of spatial modes that have to be interfered when you want them to. And so that becomes challenging. And this is basically how, this is what I'm going to talk about, how we may leverage different types of photonic integrated circuits to address some of these challenges. So in the outline, I'll first concentrate on these metro scale links where we don't need repeaters and tell you a bit about the research in my group, at least, on using silicon photonic integrated circuits to increase the key rate that you can generate between two participants in these metro networks, and also how you may overcome some limitations of hardware, for example, of detectors using different coding schemes. In particular, I'll talk a bit about a high-dimensional QKD field trial that we recently established. And so here are two examples. Here is a photonic integrated circuit. This is about, the scale here is about 3 millimeters on the side, and you can see it mounted here into a circuit board. There's a number of RF connections going to this circuit, and also fiber connections that come off here from the side. Inside of this, you can have, in this millimeter scale chip, hundreds of modulators. And here is an example of what's in this chip. This is a chip that Darius Bonandar, who's a PhD student in my group, together with Catherine Lee, have been working on, and he has a poster I'll point out later. But inside this chip is a modulator, or a number of modulators that can be used, for example, coherent one-way QKD. I'll tell you a bit more in detail about that in a moment. Here, in this network link, We have implemented optical routers that can manage up to 26 spatial modes and produce interferometers with a visibility of up to, or actually exceeding 80 decibels. So that's for the metro network. For the repeater nodes, of course, we need to put into these nodes here in a quantum repeater some form of memory. And the idea, of course, is that basically a single photon wouldn't fly the maybe hundreds of, maybe the thousands of kilometers of distance from here to here, from Alice to Bob. So we break the problem up into smaller chunks. And at every repeater node, we have some number of quantum memories that can talk to photons. And we try to send photons between them to establish some entanglement between two memories. For example, here was successful on this link. This is heralded. And here was successful in this attempt and unsuccessful in these attempts. So we record when we were successful. And then an important challenge of the repeater is that we need to implement an entanglement swap operation between those memories that were successful. So in this case, between the memory here and the memory over there. So this requires an efficient entanglement swap operation. That's one of the key challenges that still have to be overcome to actually enable the first quantum repeater. There isn't a quantum repeater demonstrated to date. But the difficulty here, one difficulty, is that you can't wait to send one photon to the next person, twiddle your thumbs while you wait if he's received that photon. You need to send photons like a machine gun all the time. And that means you need to have many memories at ready. And that, in turn, means that you need to have a way to interface with many memories. You need to have large switch networks. And that's really challenging, to build efficient switch networks using classical optics. And so I'll tell you a bit about how we can use our integrated photonics to build large switch networks and to couple them, these large switch networks, to atomic-like quantum memories. And in particular, in my group, we're working on NV centers and diamond, so we use electron and nuclear spins. But probably similar networks will be useful to other kinds of systems as well, like trapped ions or neutral atoms. I'll also talk very briefly and then refer you to a talk by Mihir Hunt about a recent analysis we did on a different kind of quantum repeater memory, which consists of an optical cluster state. And this work was based on some really nice work from the group of Taekwondo, and we looked at how we may implement that on these photonic circuits that we built in the laboratory. And we'll show you that, we've done some calculations that we'll report on here on what the resource costs are to build a cluster state that's sufficiently large that it can beat the repeaterless quantum Comm bounds that we've already heard about earlier today. All right, so to the first point, so repeaterless QKD has really grown up, which is nice to see, but ultimately it will be bounded. There's nothing you can do without a repeater to break, at least in one-way communication, transmission of quantum states, this bound on the fundamental rate loss scaling. And we've already heard about that before. So here is a variety of number of different QKD protocols. And actually, it's pretty cool, I think, that the BB84 protocol is actually doing quite well in terms of secret key rate or bits per channel use compared to the ultimate bounds. Here are some of the other protocols that are maybe like a factor of 10 or so away from the ultimate limit. To get to, at a certain distance, 100 kilometers or so, to come to here get a better than 0.1 bit per channel use, you have to use some form of repeater. And in fact, that's a good working definition based also on the work of Saika Guha and others that we can use to define what a quantum repeater is. It doesn't necessarily have to be something where the rate scales polynomially in loss, but something that beats the repeaterless bound. Excuse me? Single photon BB8, sorry about that, yeah. So this is perfect, by the way, it's assuming a perfect single photon source, 100% efficiency into the channel. So I looked at some of the recent QKD demos and calculated the bits per mode that they get and compared it to this limit that Stefano predicts. And actually there's quite a gap in between the theoretical limit and the actually achieved experimentally achieved bits per mode. And this, of course, has to do with imperfections in the transmitter, in the detectors, probably finite key corrections, and so on. But the point is there's quite a lot of limit. There's quite a lot of gap that we have to increase the key rates that we can achieve. And so one of these gaps is detector saturation. And here's a sort of a typical plot of a QKD system that shows three regimes. One, in the low loss limit, you're typically limited by how fast your detector can reset itself. Then you have the sort of the exponential loss in rate due to channel loss, and finally it plummets because of dark counts. But here there's a gap because a detector can only click so many times. So for example, here we assume sort of normal, 10 gigahertz modulation rate on the transmitter and so on. And the point is that for low loss, and this could be even less than 100 kilometers, so it's not like necessarily an extremely small distance. In a metro network, you're often limited by the fact that your detector can only click maybe 100 million times per second or so when it gets to saturation. You should be well below that in reality. And so there's this gap. And so what we've been working on is looking at how we may actually increase, given the detectors that you have, how we may increase this rate at low channel loss. And so one way you can do that is to use high-dimensional encoding of photons. So rather than encoding a photon in two temporal modes, and we call that here M, the dimensionality of the Hilbert space that the photon sits in, rather than breaking your time up into binary states, leading or trailing photon, you can have larger and larger Hilbert spaces. And sometimes, when your channel loss is low, and you can only make so many clicks per second, you can make up for some of this inefficiency in the detector by just going to a larger Hilbert space encoding. And so we looked at this protocol. The challenge here is really to make measurements in two conjugate bases, in two mutually unbiased bases. One way to do that is you could measure in temporal mode and in spectral modes. These are mutually unbiased. But that turns out you need a spectrometer maybe which requires many detectors. So maybe a more efficient way to do that is to instead produce two entangled photons, and you measure them either directly in the time domain on Alice's side and Bob's side, or you can measure in a mutually unbiased basis, which rather than going through a spectrometer, you can achieve by going through normal group velocity and anomalous group velocity dispersion, which shifts a photon based on its spectrum. So it's in effect sort of a measurement of the spectrum by the arrival time. And so we've looked at the security of this kind of a protocol against collective attacks and extended it to decoy states. So a way of limiting side channel attacks in high-dimensional QKD. And we've done recently some laboratory demonstrations. This work was done in collaboration with these people at MIT and at NIST. So now I want to show you a recent version of this high-dimensional QKD protocol that we implemented in a Boston area quantum network testbed that we've been working on in my group together with Lincoln Laboratory over the last couple of years. And this basically consists of the following thing here. At MIT main campus, we have fibers going to Lincoln Laboratory, which is in Lexington. This is a 43-kilometer fiber. We also have fiber going to Harvard, 7-kilometer. These are dark dual-stranded fiber lengths, and that from there on actually goes out to Raytheon BBN and Fresh Pond in Cambridge. And so the protocol is summarized here. Catherine has a poster on it. And it consists of a broadband light source that's filtered, modulated for pulse carving, and then sent either deterministically to a normal group velocity dispersion element, which spreads this photon out in frequency, sends it to Bob, or it sends it in the other basis directly over to Bob, who then measures randomly in one of two possible bases, either using anomalous dispersion that basically rephases this wave packet to a given temporal mode, or in direct detection. And so there's a related poster actually given by Ben Dixon from Lincoln on the network, how to make that network in fact phase stable, although for this demonstration it doesn't have to be phase stable. So here's a summary of the as yet unpublished results. The maximum key rate that we get in the laboratory, if no loss is between Alice and Bob, is up to 23 megabit per second after the error correction, fiber amplification, and finite key corrections are taken into account. So this is pretty fast, and I should say up front, this is not because of the high-dimensional, this is in part because of the high-dimensional QKD encoding, but also in part because at Lincoln Lab, they have very fast superconducting nanowire detectors. If you include a 41-kilometer fiber spool, you get to about 5 megabit per second, and over the deployed fiber, we're at about 1 megabit per second. So here's a summary of the secure rates that we can get in this channel for different dimensionality of the encoding. So if you see that if the channel has low loss, so 0 dB, basically Alice and Bob are connected, then an encoding with total of 16 temporal modes is optimal. But as you introduce loss, and you can see finally here with 13 dB of loss of the deployed fiber, it's best to work, as most people do, in the two-dimensional encoding scheme. Okay, but nevertheless, here's a way that you can enhance you can come closer to the channel capacity by using high-dimensional encoding. The next thing I want to talk about, how we may further increase the key rate that can be, the key rate that you can get in repeaterless network is using silicon photonics. So here's a chip, this is a wafer run that basically produces in a foundry, it produces many copies of a circuit like this, and if we as a customer go to one of these foundries, we buy some fraction of that circuit. And that costs some amount of dollars per millimeter square, but it gives us access to some really cutting-edge technology. For example, modulators can be over 10 gigahertz. You have on-chip classical detectors. We've been working on integrating superconducting detectors. We can get, in the meantime, interferometers that have very high contrast. You can produce entangled photon pairs by spontaneous forward mixing and so forth. And so basically, these silicon photonic circuits can be useful because not only are they stable and resilient, phase stable, you can pack tons of modulators, tons of channels on one of these chips, and so you can just scale up and using wavelength division multiplexing the key rate. The cost compared to off-the-shelf commercial modulators is also quite a lot lower if you do the math. And the volume, of course, is much smaller as well. But it turns out you can't exactly use these devices from the foundry. You have to tweak quite a lot to modify the performance of these devices for QKD. An example of that is in classical comm, people are happy with an intensity modulator that gets about 6 dB of contrast. For quantum, that's not enough. We need to have something more like 20 dB of contrast. So we had to devise some new components to allow for these protocols. All right, to allow QKD to be run on them. So here's one of these. Here's one of these components. This here is. So I was just talking about high-dimensional QKD uses measurements in two possible bases. Either you measure a photon directly in time, or you first send it through a dispersive element that spreads it out in frequency. Turns out we can do that on a photonic circuit, and what this is here is a series of 16 overcoupled rings coupled to a waveguide, and we can control the coupling by an external Mach-Zehnder interferometer to this internal ring, and in this way control not only quality factor of the ring, how much it's coupled to the waveguide, but also the resonance frequency of it. And if you have a photon passing by 16 of these fully tunable in Q factor and frequency rings, you can change the dispersion. In fact, you can program the dispersion that you want. And so, for example, here is a group delay that we can just program in from when the devices first turn on, the group delay is random. Suppose we want to have a linear group delay for group velocity dispersion, and we can just program that, and that's the experimentally measured curve here in blue. So now you can have Alice have normal group velocity dispersion, and Bob have anomalous group velocity dispersion for their measurements. Another device that we've developed is a photonic integrated circuit that I've already just briefly flashed for coherent one-way QKD, and we're also intending an experiment on measurement device-independent QKD. In both cases, basically, the requirements on the modulators are much the same. So here you have light going into, just consider these two circuits, light going into these waveguides. There's photodetectors here on the chip that allows us to monitor the intensity of the light. And these modulators here can drop light into this output channel. And in this way, we can pulse carve either in the leading or trailing time bin, or in the superposition of the leading and trailing time bins, with a phase that's set by the path length, which is monolithically defined on the circuit, the path length between this and this ring. It's some tens of microns path length difference. We can tune that in at a certain temperature to produce the pi and the minus pi offset in the phase. So here's the chip that we use for this, and here's a recent demo that shows, at the moment, there's a poster also here by Darius. At the moment, we get some hundreds of kilobit per second. So this to us is actually considerably slower than we were able to do using off-the-shelf components. And the problem here is still that the modulation depth of these modulators, which were not fully optimized for QKD applications, wasn't high enough. It was only about 15 dB, and they had to be run in forward bias rather than the reverse bias. We now have a new generation of modulators that should allow us to go about 10 times faster in the rate, and they should also have a much lower bit error rate than what we had here. So we think we should be able to match or exceed the performance that we currently get using off-the-shelf modulators. So some tens of megabit per second with zero channel loss should be possible. This here was just between two buildings, a short fiber between these two. All right, and the final place where photonic integrated circuits can help that I want to point out is in switches. So, for example, for measurement device independent QKD, you probably have many participants who want to have Charlie make Bell state measurements on their transmissions going to Charlie, but you have to navigate many different users of the network. And so one way you can do that is using these photonic routing circuits. And I've already talked about them briefly, so here's a little bit more depth of what they look like. Here's a wire bonded chip. Here's basically a schematic of that chip. You can see here a total of, actually it's 26 input modes. So you could talk to 26 users, and you can route all of these guys, which are Mach-Zehnder interferometers with very high visibility. We get more than 80 dB of visibility in the contrast of these interferometers. You can route light from this user with any of the other users together to do a Bell state measurement here at the end if you send this to photodetectors. And so here's this chip in action. And you can see, for example, here we send in very intense light, and you can see some of that light leaking out to a camera. Normally in operation, you wouldn't see this because we would be working at single photon level. We haven't done that experiment yet, but we're gearing up for it. Here is, in principle, you could also use photonic integrated circuits with the detectors directly integrated on the chip. And here's a demonstration in a collaboration with Carl Bergen's group at MIT that places 10 functional superconducting nanowire single photon detectors based on niobium nitride directly on one of these silicon photonic circuits. And you can see each of them works pretty well with about 50 picoseconds of jitter and an efficiency of some tens of percent. All right, now I want to move on to, how much time do we have? 5 minutes? Until the 5 minutes, right? Now I want to move on to how photonic integrated circuits can help in repeater networks. All right, so remember this, so I had this slide here earlier, so basically with a repeater network, what we need to do is herald entanglement between distant memories, maybe some tens of kilometers apart, and then implement Bell state measurements or so to produce these entanglement swaps between memories that were entangled to their neighbors. And originally in the proposal from Briegel and others, we just considered matter qubits. And all of these would be, let's say, internal states of atoms. This is actually, in many respects, that's great, although still technically very challenging, because as far as I know, there hasn't been a demonstration of an actual quantum repeater to this day. So it's certainly not trivial. But a lot of the components are coming along nicely, and I think we could expect that within the next few years, maybe the first demos of these systems will be implemented, and then it's going to go into scaling, how to make not one, but 100 or 1,000 of these guys work well together. But there is a challenging part, which is the photonic interface. How do you get a photon in this hybrid network to efficiently talk to the internal state of an atom? And maybe it also requires frequency conversion, which adds further inefficiencies. It would be super awesome if somehow we could just use photons directly as our memory. And so we looked at, with Saikat Guha, very closely at this really nice proposal from Azuma, Tamaki, and Lowe that came out last year on replacing the atomic memories with photonic cluster states. And the reason why you need a cluster is that, number one, you can produce some form of error correction so that your photons live longer, the qubit in the photons live longer than they would decay in an optical fiber, and 2, so that you can efficiently make these Bell state measurements to do the entanglement swap efficiently enough. So this is a pretty busy slide, I apologize for that, but that's the basic thing, and I want to direct you to the talk that, that Mihir Pant is going to give tomorrow, and also to this archive paper with Saikat and Hari Krovi. Just very quickly, we basically looked at, if we assume sort of this photonics integrated circuit technology that I already showed you, and we say, well, how good, based on the assumptions of the PICs, how well can this type of protocol work based on waveguide losses, switching efficiencies, all the other stuff that goes into it? How well can that proposal work? And it turns out if you just use the proposal directly, you would need about 10 to the 9, Saikat, correct me if I'm wrong, I think 10 to the 9 or so photons to produce a cluster state that's large enough to beat the repeaterless bound, 10 to the 9. Pretty hard. Then we, and Mihir, put in some optimizations. We now use boosted Bell state measurements and tree networks to make these cluster states more efficiently. And that reduced the complexity down to maybe about a few 100,000, based on 99% detector efficiency, which comes close to where we're going to be fairly soon, I would say. Aggressive, but not irrational assumptions on the technology. You still need maybe 100,000 or 200,000 photon sources on every repeater. Okay, it's not easy, but you can see the kind of things that we're up against technologically. And here are the assumptions on the devices, okay, based on our measurements. I should say that if we further improve the devices we have, for example, if we had an on-demand Bell state source, you could reduce this down to about 1,000 Bell states to produce one cluster that's large enough to repeat the repeaterless bound. And if you also use quantum parity codes or other tricks, you could reduce that number down further. Okay, so maybe, it's not so unrealistic. So the other way, in the more traditional way of making these repeaters, is to use atomic memories. And there's many different memories that are being explored. And I want to talk very briefly in the last few minutes about our effort on integrating nitrogen vacancy centers into chips for these repeaters. Now, the NB has sort of a nice feature to it, which is that you can couple a photon efficiently to the electron spin of the nitrogen vacancy center in diamond, and then transfer the spin information of the electron onto a nearby nucleus. You do that with the next partner over and transfer that onto the nucleus as well. Now you have two nuclei, these are carbon-13, sitting real close to one another, which are pairwise entangled to their neighbors. And that allows you to do the entanglement swap operation much more efficiently because they're already coupled. And that's a nice feature for actually implementing a full quantum repeater. So we're pretty hopeful that this in principle can work. And here's a really nice work from the group of Ronald Henson at Delft that showed actually sort of a half repeater. They showed the entanglement of 2 electron spins over 1.3 kilometer distance. That together with efficient swap gates could maybe realize one of these repeater networks, but the problem is that at present the 2-photon protocol is still quite slow. It takes maybe hours or days or so to produce entanglement between electron spins over this distance. So what we need to do is to make the coupling more efficient between electron spins and NVs and photons. And so in my group, we're working on these photonic crystal nanocavities that are coupled to electron spins that should improve the coupling efficiency by hopefully about an order or 2 of magnitude. And these are 2-photon protocols, so your efficiency goes square as the improvement. And so you've already seen this kind of network. Here, just very quickly, some slides on where we are. So you can see here, you can make an NV that's normally has this ugly phonon sideband, well behaved optically. Here's the 0 phonon line of the emission of the NV center. And we now get the majority of light into the 0 phonon line of the NV, whereas normally it's just a few percent. We can integrate multiple NV centers deterministically into a photonic integrated circuit. The photonic integrated circuit in this case is a backbone made of another material, in this case silicon nitride. We can integrate that, and the performance of these memories are pretty good. So the coherence time is some hundreds of microseconds. It's as good as the parent crystal. If we used pure diamond, We have, and others have already shown that we can get to sort of tens of milliseconds of coherence time. In our case, about 3 milliseconds, I should say. And the optical line widths are pretty promising. They're close, they're about, at the moment, about a factor of 20 or so from Fourier transfer unlimited, and we have some more work to do to improve the optical qualities. But if we can do that, if we can, make these optical links more efficient, then hopefully we can entangle faster than the coherence and actually begin to build these larger networks. Some of the other things that photonic integrated circuits allow you to do are shown here. You can make, by the way, here's how we couple between diamond and the underlying silicon nitride waveguide. And if you make the underlying chip separately, you don't have to make any compromises in the fabrication. We can integrate into the chips, pretty good filters that we need. We can integrate electrical connections and RF connections and so forth. All right, so here's my summary. We want to somehow find ways to more efficiently transmit quantum states. We're interested in doing this in two regimes. In the metro scheme, we've implemented this high-dimensional quantum key distribution protocol that allows us to get more than 1 bit of information per detected photon. That gives us some boost, but I should say it's just a logarithmically increasing boost by the size of the Hilbert space. But nevertheless, some boost over a two-dimensional protocol. And we can get, for example, up to more than 20 megabit per second QKD rate with fast detectors. And then in the small network, in the ground, with 13 dB of channel loss, we were able to get more than 1 megabit per second of secure key rate after privacy amplification, finite key corrections, and so on. Going forward, we think that photonic integrated circuits can help, for example, in the high-dimensional QKD by programmable dispersion devices, by making wavelength division multiplexed QKD transmitters. So with this type of device, you could run over tens or hundreds of channels simultaneously. And basically, that should be the same factor that you could increase the key rate. You can do switching arrays. You can integrate superconducting detectors. And on the repeater side, I think it's still not totally clear what the best way forward is. Repeaters are still an extremely challenging thing. Maybe with the right optical devices, you may be able to produce large enough optical cluster states, in which case you can just do all your repeaters at the same wavelength as your channel. And then there's also some work to be done on interfacing in an efficient way with many quantum memories on chips. And I think this is another area where these photonic integrated circuits can play a big role. Okay, so that's what I have. Thanks a lot. Take some questions.
Okay, so we have time for a couple of questions.
There's a,
Thanks. What is your switching speed of your switches, and what is the limitation?
Yeah, so we have two kinds of modulators for switches. The first type uses free carrier dispersion. And basically, there, the refractive index change is achieved by either injecting or depleting some electron gas into the modulator. When you do that, there's no way of getting around also absorbing some light with this electron gas. And these modulators have some fraction of a dB per modulator loss, but they can go at tens of gigahertz. There's some recent ways that you can actually heavily bias silicon photonics to make directly an electro-optic modulator that looks promising, that could push down these losses and still give you the same speed. The devices that we're developing now for the NV centers are based on aluminum nitride, which has a Chi2 coefficient and is directly usable as modulators. And in their case, there should be no loss. There's no free carrier dispersion. But the downside is that the modulators tend to be a little bit bigger. So this is for high-speed modulators. Typically, with high speed, I think you're going to incur some amount of loss. The switch arrays that I've shown actually use thermo-optic modulators that operate at about a microsecond switching time. So considerably slower. But in a network application, oftentimes it's fine, right? If you just want to allocate modes to different users. A microsecond, but the benefit of that is the thermal optic modulator is essentially lossless. So we see basically zero loss with one of these modulators.
One of your tables showed chip-to-fiber coupling efficiency of 0.99. How realistic is that?
Yeah, so we have different strategies. I mean, we silicon photonics people have different strategies for coupling to chips. One, in the case of an edge coupling, you basically mode match of optical fiber to the edge of a chip, and you can actually get well under 1 dB transfer efficiency. I think in the next couple of years we have some chips that should likely go like 0.1 dB or so coupling loss. Also, some recent work out of the University of Colorado showed that even for vertical couplers, you can get about 98% or so coupling efficiency, even in practice, by optimizing the grading design so that the coupled mode is very close to a Gaussian and therefore overlaps well with the fiber. So the numbers here we showed we assumed are actually a little bit, I would say, are a little bit conservative almost, because we assumed we wanted to couple to many, many modes. But basically soon, I mean, actually in our chips at the moment, we get maybe 2 dB of coupling losses, but I think very soon you should be able to go well under 1 dB, and people are beginning to do that as well. Yeah. Last question, maybe?
One more, and then that's it, I think.
The diamond which looks at room temperature or
Oh, yeah, they're all cryo. They're 3 Kelvin, yeah. Yeah. Okay, thanks.